Now let's try to understand time dilation intuitively again from the perspective of the postulates of special relativity. So let's consider a static clock in frame S. And one way we can construct such a clock is to imagine what we call a light clock. So now suppose that this rod has, you imagine a setup where I have two mirrors, so one mirror here and one mirror over here, and I shoot a light beam upwards, okay, and the separation between them is known, of some length L, and this light beam goes up and gets reflected back down, and the time it takes to travel up and back down, I call that time 2L by C. Okay, so by measuring how many clicks I register on, so if I wait some amount of time, any light beam that I send up will bounce up and down many times. So if I count how many 2L by C, how many clicks I register, okay, the total time would be number of clicks times 2L by C. Okay, so I can measure time in this way using this device, which we call a light clock. And again, the reason to use a light clock is there's nothing special about a light clock. Everything that we say should be true for any kind of clock that you use to measure things. However, we can be sure about how the light clock appears to behave relative to a second observer, S prime, who is now moving with respect to S at a speed v. Okay, and the reason we can be sure about this is because we know how light appears to behave according to the postulates of special relativity as seen by a moving observer. Okay, an observer moving relative to this light clock. So now let's suppose that we have S prime is also carrying a clock with them. S prime is also carrying a clock, which is also a light clock. And so they send light beams up and down. And let's suppose that the length L that they have is the same in the rest frame of the train. And again, the time that they measure on their clock would be the number of clicks that they see times 2L by C. Now, you might be concerned that if the time interval 2L by C is large, right, then we will only be able to measure time with some resolution, right, because we have to wait for the light signal to actually register a click. But in principle, we can make this length L as small as we like, and therefore we can measure time with arbitrary precision by choosing a small enough length in the perpendicular direction. Now, what we'd like to know is if, let's say, the clock on the train registers one click, that is, it registers a time interval of 2L by C, that is one click, how much time would have elapsed on a ground observer's clock in the time it takes for the train observer's clock to register one click? So what we would see is, if you were in the frame S and you look at this moving light clock of observer S prime, the moving light clock looks like this. There's a light signal that's sent, and the light signal would appear to travel forwards and then down, and the light clock is moving along with this. So the light clock over here is where the light hits the reflecting surface, and then over here is where it comes down and registers a click. Okay, so this is what S prime's light clock would look like in the frame S. Okay, and remember that in the perpendicular direction L, the length of the light clock perpendicular to the direction of relative motion would be exactly the same. So both observers would agree that in the perpendicular direction, the light has to traverse exactly the same distance. However, they disagree on the distance traversed by the light in the horizontal direction. According to the train observer, okay, the light has not moved at all in the horizontal direction. It's just gone straight up and down. I've shown it here as separate, but really you should think of this as I sent it straight up and it came straight back down. Okay. Okay, so now we can ask, according to the ground observer, how long does it take for the light signal to go up here, okay, to go up here and then come back down? Now, in the suppose it takes a time interval delta t for this light signal to go up and come back down. In this time, the train or the clock would have traveled a horizontal distance of v times delta t. All right, and now we know in the perpendicular direction that this length is L, okay, and since the situation is symmetric, this distance is v delta t, half v delta t, and this distance is also half v delta t. So therefore, by using Pythagoras' theorem, this is a 90-degree angle, this distance over here is just the square root of L square plus half v delta t whole square. Okay, and similarly, this distance is the same as well. Okay, it's the square root of L square plus half v delta t square. So therefore, the observer on the ground concludes that the light signal that observer S prime sent, or observers on the train sent with their light signal, actually traveled a distance. So distance traveled by the light signal on the train as seen by the ground observer, or as seen on the moving clock, as seen by the ground observer, appears to be twice of the square root of L square plus half v delta t square. But how long would it take for light to travel that distance? Well, we know the answer from the postulates of special relativity. No matter which direction this light beam is traveling, it should be traveling at a speed c as seen by the observers on the ground. It appears to travel at a speed c on the train, but it also appears to travel at a speed c according to the observers on the ground. So therefore, it must be true that this light signal travels at a speed c. So another way to express this distance that the light beam travels, so the distance should also be c times delta t. That is, this expression for the distance should be exactly the same as this expression for the distance. So equating these two, we can actually figure out how much time delta t would have appeared to pass for the ground observer. So equating them, equating these two expressions tells us how much time has passed for the ground observer. Okay, and that time would be 2 times the square root of L square plus half v delta t square over delta t. Okay, so this is the distance that the light beam travels divided by the time it takes to travel that distance. This should be equal to the speed of light. Okay. I'm sorry, there should be a square on the whole thing, half v delta t the whole square. Now, this is a quadratic equation with two square roots, or two solutions for delta t. And obviously, we're going to take the positive solution. And the positive solution is just delta t is equal to 2L over the square root of c square minus v square, which can be written as 2L over c over square root of 1 minus v square by c square. Okay, and this is nothing but 1 over the square root of 1 minus v square by c square is gamma. So we can write this as gamma times 2L over c. But 2L over c is the time that the train observer registers on their clock. Okay, so the train observer has concluded that for one click, the time interval that has passed is 2L by c, because they saw one click. So in other words, this is gamma times delta t prime. Okay, so the time that has passed on the ground compared to the time that has passed on the moving clock is related by this factor of gamma. The time that has appeared to tick on the train appears to be smaller than the time that has ticked or has passed on the ground. So this is the phenomena of time dilation as seen intuitively by using just the postulates of special relativity. Now let's see how we can use the time dilation result that we just derived intuitively to understand length contraction when the motion of a rod is perpendicular or is parallel to the direction of relative motion. So let's suppose that we have a platform of length L as measured in the frame of the platform, which is at rest. Okay, and now suppose you have a train passing it at a speed v, and let's suppose that an observer on the train wants to measure the length of this platform. So now, as they pass the platform, so let's imagine that the way they measure this is, let's take a particular observer on the train. So let's take this observer sitting at this end over here. And let's suppose as they pass the platform, okay, as they pass the platform, they will note the time on their clock. And when they reach the other end of the platform, they will note the time on their clock. And since they see the platform going in the opposite direction relative to them, they would conclude that the platform has a length L prime, which is v times delta t prime. Okay, so this would be the length measured by the train observer. Now, this clock, which is moving with the train observer, appears to have time dilation as seen by the ground observer. So according to the ground observer, the time delta t prime that is ticked is actually equal to v times delta t over gamma, where delta t is the time it takes, as seen by the ground observer, for this person on the train to pass one end of the platform and then pass the second end of the platform. Okay, and since the train is moving at a speed v, the time or v times delta t should just be the length of the platform. Okay, So v times delta t should be the length of the platform. So therefore, the length as measured by the train observer is L over gamma. That is L times the square root of 1 minus v squared by c squared. In other words, since the platform appears to be moving relative to the train observer, the length of this platform, as measured by the train observer, appears to be smaller than L. Okay, so this is the phenomena of length contraction parallel to the direction of motion. So I want to point out one important way in which we used this time dilation effect here. The important thing was to use the same moving clock. That is the clock that is with this particular observer that has moved now from one end of the platform to the other end of the platform. All right. The clocks that are used on the ground to measure the platform's length are not the same clock. There's one clock located at one end, another clock located at the other end. We know the separation between these clocks, and we make a simultaneous measurement of on these clocks. Okay, so these are not the same clock which are being used to measure, let's say, the length of the platform or any object that's passing by the platform. And when we used the train observer's clock, the clock on the train, that was a single clock that was moving with a particular observer on the train. And the time dilation effect is related to a particular clock moving along or moving relative to a different reference frame, in this case moving relative to the platform.